Okay, let's see if I can.
There's something overlaying it a little bit. Yeah. That.
Okay, is it moving down now?
Yes.
Okay, so in the basic definitions on this first screen, you see my arrows?
I can see you moving the cursor. Yes.
G11 and G3. Okay, so the first thing is, again, defining a nilpotent is just any algebraic quantity with not equal to 0, such that x squared is equal to 0. And then I make the assumption that these nilpotents are to be added and multiplied using the same rules of addition and multiplication as with real or complex matrices. Okay. And
I have a couple of comments as we go along. One is I was sometimes confused in your document about which algebra you were referring to. So when you talk about the nilpotents as being an element of a Grassmann algebra, so in that case, the multiplication that we're talking about is the Grassmann multiplication that's part of that Grassmann algebra, right? Whereas later,
I'm assuming an algebra which I haven't said anything about yet, and I'm assuming, so I'm defining what a nilpotent is, and I'm assuming the algebra I'm going to define has the same rules of addition and multiplication as the rules of matrix algebra. So a nilpotent is just an element in this algebra which I haven't really defined, which has square 0. And I can add and multiply these nilpotents according to the rules, the usual rules of matrix algebra. In fact, I'm going to generate an algebraic isomorphism with matrices as being coordinate matrices that correspond to geometric algebra, which I'm going to define in terms of dual Grassmann algebras. Okay. Do
you need anything other than the fact that these are not, it's non-commutative?
No, I don't. All I need is the idea of a nilpotent, which has square 0. And I'm saying that we're going to add these algebraic quantities and multiply this using the same rules as matrix algebra. Now, then I define the second point here, two nilpotents, which I call A1 and A2, have to be anti-commutative times A2 plus A2 times A1 is equal to 0. So that's just the definition again. Okay. And then now is when I'm defining a Grassmann algebra, a set of mutually anti-commuting nilpotents, which I take n of them, A1 up to AN, is said to be linearly independent over the real or complex numbers. If you multiply them together, you don't get 0. It's non-zero. And in this case, then they generate a 2 to the n-dimensional Grassmann algebra. Okay, so I'm really defining a Grassmann algebra of nilpotents. So I am assuming they're nilpotents. Normally, elements of a Grassmann algebra aren't called nilpotents, but of course they are. You define the wedge product, but I'm not using the wedge product. I'm just using the product of these nilpotents because it is a Grassmann algebra. Of course, the dot product would be equal to 0, but I'm just saying that a nilpotent has square equal to 0. So you have two nilpotents. They're said to be anti-commutative. A1 times A2 plus A2 times A1 is equal to 0. Of course, that just says the rule A1 times A2 is equal to minus A2 times A1, the usual definition for the Grassmann product of two elements, which I call nilpotents. because I did assume that x squared is equal to 0. And defining a Grossman algebra, but in terms of the basic generators of the Grossman algebra, which I call nilpotents because they have square equal to 0. So I guess I'm doing things in a little different way than people normally do. So a set of, again, I'll read that. A set of mutually anti-commuting nilpotents is said to be linearly independent if the product of these things is not equal to 0. In this case, they generate a 2 to the n-dimensional Grossman algebra. Okay, now the next definition is very important. Now I choose
Excuse me, Professor. One question. In the elements of the Grossman algebra that you are using, not all the elements are nilpotent. Is that right?
No,
but some of them are.
No, they're all nilpotents at this point. But now, yeah, this definition 1 here, a pair of nilpotents are said to be algebraically compatible or dual if AB plus BA is equal to 1. Okay, so that's a new definition of what I mean by dual, or what I call algebraically compatible, because what I want to do is basically put two Grossman algebras together. Okay, a pair of nilpotents, A and B, are said to be algebraically compatible if you take A times B plus, and of course now that's where I haven't limited. So the Grossman algebra GNF is generated by n mutually anti-commuting nilpotents. Okay, so that defines a Grossman algebra. It's essentially equivalent to a Grossman algebra. But now I'm going on and I'm defining something. These nilpotents are more general than just a Grossman algebra now, because I'm saying a pair of nilpotents are said to be compatible. When you take AB plus BA, you get equal to 1. Well, okay, so 1 is just the standard real number 1.
So that's the point at which the question arises in my mind, because I'm thinking in terms of an algebra as being defined by its multiplication, whereas you are thinking of, I don't know, elements independently, like maybe elements in some non-commutative algebra, but the algebra is unspecified. So when you write A, B, my question is, well, where's the multiplication? Like it's not a multiplication in Gn
that's right.
Generated by A, and it's not in the algebra generated by B, right?
That's right. So the Grossman algebra is generated above that by n mutually anti-commuting nilpotents. Okay. But now I'm going beyond. So that's right. I'm talking about an algebra which is larger than the Grossman algebra. You can think about the Grossman algebra as being a subalgebra of this larger algebra, which in fact is just isomorphic to the common n by n matrices. That's the point. So I'm actually defining what I mean by compatible. You can think about as being in a matrix. In fact, that's what I do in this definition 2. Okay.
Can we say, for example, that A is element of the Grossman algebra, but B is not element of the Grossman algebra?
That's right. It's not an element of the Grossman algebra G, which I define above equation 1.
Yes.
Because that
and then we are here making a product between elements of different space.
Exactly, yeah. So
exactly.
In fact, if I go down a little further, you can see Okay, look at this multiplication. So here I have a pair of nilpotents, which I call A and B. Okay, so A times A is equal to 0. B times B is equal to 0. B times B is equal to 0. If I multiply A times AB, well, remember I'm using the rules of multiplication, so A times AB is the same thing as A squared times B, but squared is 0 because it's a nilpotent. So A times AB is just equal to 0 because A times AB is A squared B, but A squared, I assume the laws of matrix multiplication, so it's associative. So I can write that as A squared, so I get A squared is 0 times B. Okay,
Yeah,
well, that's 0 then.
A
But
square
no,
yes, because A square should be 0. So A square B is like 0 multiplied by B.
yeah, A times AB is the same thing as A squared times B, which is 0 times B, which is 0.
0 times B, exactly, which is 0. Yes, yes.
Okay,
But
and look at this.
excuse me.
A times BA. Look at A times BA. Now I'll go back to here.
Okay.
If I take this equation 1 and multiply it on the left by A, then I get A times A. I get A times AB, which is A squared times B, which is 0. Then I get ABA equal to A. And that's how I'm defining the multiplication then, that ABA is equal to A because I'm multiplying on the left by A. Okay, and I assume the laws of ordinary matrix multiplication. So I get A squared times B, which is 0, and I get ABA, and that whole thing is equal to A then. Okay, so that's how I get this table. A times BA is equal to A. I get it from that compatibility condition. AB plus BA is equal to 1. I multiply that equation by A on the left. I get A on the right, but I get A squared B plus ABA. Okay, so that's why I get A times BA is equal to A. Okay, and now we have B. B times A is BA. I don't say what that is because I haven't said anything about it yet. But I have B times AB is equal to B. Well, why is that? Well, I'm multiplying on the right by B. So I get A times B squared. Well, that's 0. So I get BAB is equal to B. Okay.
Yeah, all of that's very clear, I think.
Okay, so that's
but I do have a question though. If you skip back a little bit, just in the previous bottom of the previous page, where you introduce the coordinate matrices. That's the this is
yeah.
or maybe even the reference to the word spectral basis.
But here I'm
that
identifying.
goes by very quickly.
Yeah. Okay, here I'm identifying I'm saying the matrix of the nilpotent A is this matrix 0, 0, 1, 0. Okay, I call that matrix of A. The matrix of B is a matrix 0, 1, 0, 0. Well, you can see if you square these matrices, you get 0.
Yes.
Okay.
Yes, indeed.
And now look, if I take BA, well, look at this. Look at the table here. BA times BA equal to BA. So that's an idempotent. Well, how do you prove that? Well, here, multiply AB times this equation 1 again. AB times AB is AB squared plus AB BA. But again, AB squared times A is 0. You get AB squared is equal to AB. So it all follows from this condition of algebraically compatible. Okay,
But your equation number 2, the spectral basis. I mean, when you write that out, I've I sort of found that sort of a little raw, maybe. Like I don't understand why you write this spectral basis in this way. Like it's
Well,
in what you wrote.
It's by three. Look at equation number 3. So if you have this matrix G11, G12, G21, G22, note that G1 corresponds to BA, because it's G1 times BA plus G12 times B, that's this element, plus G21 times A. Okay, that's G2 times this element down here. Well, that comes from this nilpotent. You know, do you understand that? So this spectral basis, the matrix of G, G11, G12, G21 for real numbers.
But spectral basis, when I try to understand what you mean by that, I'm looking at the solution of a polynomial, right? And I'm looking for some minimal polynomial.
Well, here I'm defining what I mean by a matrix. So in other words, I'm taking the Grossman algebra as being more fundamental and compatible. Well, this is the simplest case of compatible. So I'm taking a nilpotent as being more fundamental than a matrix itself. In fact, you might say that Cayley, instead of inventing matrices, Clifford could have invented linear algebra based on nilpotents and Grossman algebra rather than the other way around. So really, you can say, why wasn't Clifford algebra? Clifford algebra was invented before matrix algebra, but they are never connected together in this way that, well, you can read the literature. You know, Hesnes wrote a paper about nilpotents and relationship, but they never gave it in this nice, simple form that I'm giving here. So that.
But why call equation number two? Why call that a basis, like spectral basis?
Well, I'm calling it a basis, the matrix G11, G12, G21, G2, because the geometric number corresponds to this element, G11BA plus a real number times this basis element B, these are all nilpotent. Well, BA is a product of two nilpotents, which we have seen as an idempotent. In fact, it's the idempotent corresponding to, it's just the 4 elements of a matrix, okay? A is a nilpotent because the matrix of A has square 0. The matrix of B has square 0, right? It's clear, matrix multiplication.
Yes, this part's very clear. But what wasn't, this looks very clear. But what didn't seem clear to me is your immediate reference to number 2 as being a basis, as being a spectral basis. And when I look at 2, I don't.
That's how I'm creating.
You state with respect to the spectral basis, and then it's as if I should understand immediately that this is a basis, and I don't.
Yeah. Okay, look at my equation on the left here. Remember, BA is an idempotent. So if I multiply B, I can actually put BA, multiply BA times 1, I get BA. And if I take BA times AB times A, I get ABA, but we saw from the multiplication table that that's equal to 1, 2, right?
Mm-hmm.
From this table here. So I'm doing this matrix multiplication. That's a nilpotent, so I can put it on both. So if I multiply BA times 1A, I get BAA. Okay, now if I multiply BA times 1, and I get BA, and then BAB is B. So you can see how I get from this step 1A, BA, 1B to BA times BAB, right? You understand that, right?
Yeah.
Okay.
Yes, that seems clear.
Now I multiply this out. So I'm using the rules of matrix multiplying a column vector times a row vector. So BA times BA is BA. BA times B is B. ABA is A, and AB is AB.
Yeah, this is clear. I have a question for me to understand a little bit deeper. Now, the original notion of nilpotent that you introduced is defined over a field of characteristic 0. Because if you assume a characteristic non-zero, I notice here you have a mention also in the footnote, then there are all sorts of very complicated hidden degrees of freedom. So you do define the original notion of nilpotency over a characteristic, over a field of characteristic 0. Is that correct?
Over characteristic, that's right. Yeah, that's right. Characteristic 0.
If you do, then all the equations you have presented have a unique, my modest view, they have a unique interpretation, your interpretation, which I agree. But if you admit field more general fields, then it's like bombs eating variables.
Well, of course, we are talking pretty general. As long as the characteristic is not equal to 2, it's okay. You can define Clifford algebras over characteristic of prime not equal to 2, like 3 or 5 or 7, or powers 2, 3 cubed, for example. You know, they all define. In fact, Lunesto has talked about Clifford algebras over finite fields. Okay, you can, but take any finite field other than the characteristic 2. Okay, because that you have trouble defining a bivector with characteristic 2. That's the problem.
I agree that the moment you admit characteristic 2, you void your notion of a nilpotency automatically. Yes.
Well, that's right. Exactly. That's the problem. Okay. Anyway, you can understand how 2 is a basis of a geometric, a 2x2 matrix then, because this 2x2 matrix is identified with this geometric number, G11BA. So that's BA, BA, AB is a basis for the matrix 2x2 real matrices or complex matrices. Okay. Okay, so there's a simple multiplication table. And of course, this is very trivial too. You can see how I've identified now the trivial matrices. The matrix of A is just the nilpotent 0, 0, 1, 0, B, and so on. This is a nilpotent, this is a nilpotent. Note that BA plus AB is equal to 1. Well, that's the identity matrix. Okay, but here I've identified the identity matrix as 1. So I'm thinking about, I'm really generalizing the real number system to include nilpotents. And that's what I'm trying to get at by my definitions. A nilpotent is simply an algebraic quantity not equal to 0 with the property A, that its square is equal to 0. Okay, and 2 nilpotents are anti-commutative. Well, you see, that's where I'm introducing the idea of a Grassmann algebra. Okay, generates that Grassmann. So I'm really trying to generate all of matrix algebra in terms of products of these nilpotents, an algebra of nilpotents. Yeah. So the simplest case, of course, is by the 2x2 matrix. But then I'm going to generalize it to any n by n matrix or any n by m matrix. So it's completely general. You can define geometric numbers and to be the coordinate matrix of a product of nilpotents. That's the main conclusion. So actually, an algebra of nilpotents really as basic as an algebra of matrices because they're isomorphic, algebraically isomorphic. Okay, I'm getting. Okay, these rules. Okay, but okay, notice this now. The standard basis of the geometric algebra G11 is generated by 2 vectors, which I define in terms of A and B. Okay, so I define E equal to A plus B and F equal to A minus B. And you can easily check from, again, this multiplication table that E1 squared is equal to 1. Well, E squared is equal to 1 and F squared is equal to -1. And now we define the bivector E times F. Well, you can check this is equal to -F times E. Okay. These rules can, again, it all refers back to this basic multiplication table, which is defined by, so I'm giving a geometric interpretation to the matrix algebra of 2x2 matrices over real numbers in this case, but also it's true for complex matrices as well. Okay, so what is the geometric algebra G11? Well, it's generated by two vectors, which I call E and F, which are anti-commutative. EF is equal to -FE, and E squared is equal to 1 minus F squared. And the bivector, well, notice if I take the bivector, I multiply EF times EF. By associativity, I can write this as E times FE, but I can decommute because EF is equal to -FE, and I get, we have a unit bivector which has square plus 1. Well, that's called a hyperbolic bivector because it has square plus 1. A Euclidean bivector has square -1. Okay, in a Euclidean. Okay, well now you might look at this. It's pretty interesting. Look at U plus. I've defined that equal to BA, which we know is a nilpotent. But notice how I'm writing this. I'm using the identity 1/2 1 plus A plus B times A minus B. Well, if you multiply that out, you'll find that that is equal to BA. But notice now A plus B is equal to E, and A minus B is equal to F. So I can write U plus then as 1/2 1 plus U, where U is that bivector E times F. Okay. U is equal to EF. So by doing this trick, then I can write this as 1A, BA, 1B. But now notice I can replace A plus B. Why? Because I know that A times BA, I know that BA times B is 0, so it doesn't change anything. A plus B times BA is equal to 1A. You see that, right? And I can write this as, write B as A plus B because BA times A plus B is 0, BAB is B. But now I'm rewriting this spectral basis in the form U plus, U minus, E times U minus, E times U. So it's just the same as this other basis, but now I'm writing in terms of a Euclidean vector E, which has square plus 1, and a pseudo-Euclidean vector, which has square minus 1. Okay.
But you have a nice compact definition for U plus, but for U minus.
Right here it is. U minus is 1.
But would you agree that G11 is the non-compact in conventional Lie sense or not?
G11 is just the geometric algebra generated by a pair of vectors, one which has square plus 1, one which has square minus 1, which I call E and F, and they're anti-commutative. That's the geometric algebra G11.
There's no direct connection with the Lie notion of compactness and non-compactness. I can see the distinction.
Well, the Lie algebra is of course all in there too, because you define Lie algebras in terms of the bracket operation on matrices. Well, okay, it's a bracket operation on geometry. They're algebraically isomorphic. It doesn't matter what you use. Okay, well, here it. Okay. Okay, but here I emphasize that. Okay, so E1 is just the matrix, the Pauli matrix 0, 0, 1, 1. We recognize that as a Pauli algebra, Notice that E2, what I'm doing here is slightly different. I'm multiplying F. Well, F is the matrix 1 minus 1 by I, which you can think about as a square root of minus 1. So I'm showing how the usual Pauli matrices arise from by changing what we mean by what you mean by a vector or bivector. You can choose as you wish. You know, you're not restricted to a bivector. You know, well, for example, here I'm saying the Pauli vector sigma 2, which I'm denoting by E2, is I times F. Well, okay, so it's a complex, it changes the signature of F. F squared is equal to minus 1, but I commutes with F. So I times F squared, well, it's the Pauli matrix for E2 along the y-axis, if you think about it that way. And E3 is 1 minus 1. Well, that's the usual Pauli matrix for sigma 3. Okay. Okay, the real geometric, okay. And now I'm saying the real geometric algebra G11 is a subalgebra of the geometric algebra G3. Why? Because G11 is generated by E and F, okay. E3, oh, if you take E1 times E3, then you get the same thing as F.
Excuse me, Professor Garret, but here our identification of this is, I think, in one sense arbitrary, because how I can identify necessary E2 with IF.
Okay.
Not necessary. No? Not
Look at
necessary.
this. Look at 4 here. I equal to the square root of minus 1, but I'm identifying that with the trivector E1 times E2 times E3, because that's in the center of the algebra. It commutes with all elements. So there's nothing wrong with identifying.
Because my question is because I think that if we go back to the page before where there are the principal definitions, one can say that the notation here in the product AB plus BA equal 1. Okay, we can think this how one split of the space. Then I am splitting the space in the product AB plus product BA.
Exactly.
And then one is the complementary part of the other. But if they are, how you say, algebraically compatible, then A and B are not in the same space.
No, I'm saying I didn't put any limitations on my space of nilpotents, but here I'm identifying the Grassmann algebra as some algebra of this larger space.
Okay, larger space. Okay. The Grassmann algebra of this larger space. Okay, but then in the algebra, we have not all the elements of the space.
Well, that's right. In the Grassmann algebra, we don't have all the elements in the algebra of nilpotent. Okay, let's go back here because this is the important thing I didn't make. This equation number 5. Notice that I'm saying that G11, which we identified as generated by E and F, is a subalgebra of G3. And because I'm saying is E is equal to E1, and E1 times E3, which is a bivector, in the algebra G3 is identified with the vector F in the geometric algebra G11. So in other words, what I call a vector and a bivector is really pretty arbitrary. I mean, what's a vector in G11 is the bivector E1 times E3 in G3. So it's pretty arbitrary what I call a vector and a bivector. It's a matter of thinking about it. You can think about it as a vector, or you can think about it as the bivector along the XZ axis. That's the bivector E1 times E3 defined by these Pauli matrices that we have in 4 here.
Yes. So in other words, there is no reformulation of G3 into unique reformulation of G3 into G11, because G11 is a subset of G3. Is that correct?
Yeah. Well, G11 generate an algebraically isomorphic subalgebra of G3 by using the vectors E1 and the bivector E13. So E13 behaves like F, and E1, the Pauli matrix, behaves like E. It has square 1. E1 squared is equal to 1, which is the identity matrix here. But the bivector, E1 times E3, if you multiply this times this, that's the bivector. That's identified with F. Well, here you have F is equal to minus I times E2. Well, I'm identifying with E1 times E2 times E3, so E1 times E2 times E3 times E2 gives you E1 times E3. So interpreted as an element of G1, F is just a vector, okay? And E1 times E3, well, that's a bivector in the algebra G3. So I'm emphasizing that the geometric interpretation of elements is really pretty arbitrary depending upon what geometric algebra you're talking about, but it corresponds to the same matrix algebra. Well, E1 is the Pauli matrix, E2 is I times F. Remember, F okay, where is F here?
A minus B.
Yeah, A minus B. Well, okay, here's A and here's B. A minus B is 1 minus 1 then. Okay, A minus B, so it's 1 minus 1. And you multiply that by I and you get E3. Okay, there it is, E3. No, you get E2. I times F is minus I, and that's the Pauli algebra matrix for I times F. But in terms of the geometric algebra G3, it's E1 times E3. So here in G11, it's a vector identified with a vector. And so it's a different geometric interpretation of a subalgebra of G3. But that becomes important when we look at the Dirac matrices, because remember, I'm saying that each observer identifies a Pauli algebra, a different subalgebra of G3. So what a different observer calls a vector and a bivector is different for different observers, because an electromagnetic field consists of an electric field and a bivector field. But just a charge looks just like a vector, but a moving charge looks like a bivector. Well, but to an observer that's moving, a bivector becomes just a vector. So that's Hestenes' brilliance of identifying every observer corresponds to a time-like Dirac vector gamma 0. Okay. Okay, but now I'm generalizing. So I just looked at 2x2 matrices because that's the easiest one. I understand in terms of the simple multiplication table with a simple identification of these matrices. But you can do that for any order geometric algebra. So now I want to go to the next level.
Before you skip to the next, I just want to make one side comment about U minus and U plus. Like you haven't written it down here, I don't think, but it's clear that U minus plus U plus is equal to 1, right?
Oh, yes, exactly.
Yeah. So it's a sum of two idempotents. Like U plus is an idempotent and U minus is an idempotent. And if you write U plus plus U minus, that's equal to 1.
Yeah, and look what it corresponds to here. Yeah, if you take BA, the matrix of BA, plus the matrix of AB, you get the identity matrix. So 1 is just...
Yes, and this is significant, at least for me, when I was trying to understand how what you wrote could be related to Oshevich's split operation. Like and I think Jesus also had a comment. He was referring to the sum of two nilpotents that is equal to 1, but that doesn't constitute a split of the space. But a sum of two idempotents, I think, does constitute the same kind of split as what Oshevich was talking about.
Yeah, that's right. We're writing 1 as a sum of two idempotents. So A, in this case, A, in fact, any compatible null vectors, as I defined it, are said to be compatible if the sum BA plus AB is equal to 1. And that's in any number of dimensions as well. And that's the next definition I give. So let's take the next case here. Okay. Okay. So here's the general definition. More generally, two sets of linearly independent nilpotents. A1 to AN, well, they're linearly independent, so they're mutually anti-commuting. And now we're taking a second set, B1 to Bn. The B's are all anti-commuting, so that's a second Grossman algebra. And I'm saying that this Grossman algebra is algebraically compatible or dual if for all 1 ij less than or equal to n, ai times bj plus bi times aj is equal to the chronic delta ij. So in other words, for I not equal to j, they're anti-commuting, okay? So this is really characterizing matrix multiplication in terms of this basic relation 6, relating two Grossman algebras generated by the A's and the compatible Grossman algebra or dual Grossman algebra generated by the B's. So I think this is a major oversight in the definition of duality. It's always the usual thing, it's a scalar valued function on a vector space. But this is really missing the whole scheme of things that I'm developing right here. And I think is more basic. It's a more general definition of duality than what's given by just the standard dual using a functional on a vector space is equal to 1. It's a much more powerful because you can see it's identifying the geometric structure of a general matrix as a product of this nilpotent algebra. Okay.
But excuse me, but here when you find the n linear independent nilpotents, are you generating all the space with these nilpotents, or what? What are you generating with this? Okay. Because the algebra that is within from here is inside of this space of subspace. I don't know, no? And I don't know if B are part of this space or not are part of this space.
Well, they're all in the same generalized algebra of nilpotents that we started with definition 1. A nilpotent is just an algebraic quantity which has square 0. Now the algebra of these nilpotents is generated by taking all products, sums and products, using the usual rules of matrix algebra for this large algebra of nilpotents. It can be infinite dimensional, and I'm only considering finite dimensional subalgebras of this larger space of all nilpotents, all algebraic quantities which obey the usual rules of matrix addition, multiplication of matrices, but are in a much larger space of nilpotents. Okay. So now what I have here, okay, we know that the A's generate a Grossman algebra of 2 to the n dimensions. And now I'm saying pick another set of nilpotents. One up to Bn. They generate a Grossman algebra of nilpotents. Now we say that these two Grossman algebras generated by the A's on the one hand, generated by B's on the second hand, are algebraically compatible or dual if for all ij less than or equal, greater than 1 less than or equal to the n, that ai times bj plus bi times aj is equal to delta ij. In other words, ai bi plus bi times ai is equal, just as we had for just a pair of A and B, where I omitted the indices then. So that's the generalization, which gives me all matrices then, is in, well, it's a coordinate matrices of geometric numbers now. Okay, well, here I take the simplest case. And we've already discussed the case n equals to 1. The next case, n equals to 2 times real and complex 4x4 matrices as coordinate matrices of the real geometric algebras G22 and over the complex number G23. For G22, define U1 equal to B1 times A1, U2 equal to B2 times A2. Well, these are idempotents just for the same reason that they're idempotents for A and B. Okay, now define this space as 1, A1, A2, A1, 2. That's a Grossman algebra. Now we put it in between U1 times U2. U1 times U2 is just A1, B1 times B2, A2. Okay, that goes inside here. Then you have 1, B1, B2, B2, 1. That's the dual Grossman algebra to the A's. Well, in a more general case, you have, okay. And now you multiply that out in the same way I got the previous one, you know, for the spectral basis of the 2x2.
So here again, I have the same question that I had for 2, for your equation number 2. This is just a generalization of 2, but you immediately write that this is a spectral basis, and it isn't clear to me that writing this expression in this way is necessarily a spectral basis, unless you have some other other reason. You know, like you can show later that it is a spectral basis, but when you write it this way, it suggests to me that I know immediately when I write the expression on the left-hand side of the equal sign that the result should be a spectral basis, and I'm not. I have trouble understanding why that would be.
Of course, I'm not trying to prove rigorously any of this stuff, but if you go in more details, which for example are in my book here, I'll show you my book. Let's see, my book here.
Yeah, I did try to refer to some of your papers that are available online where you define spectral basis, and that looked like a lot of work. You know, like maybe I just.
When you learn how to multiply matrices, you know, it becomes automatic. Well, that's what I tried to make this simple table. It's pretty automatically how to develop the table. And we can.
Yeah.
We can
Well, this is clear. This is clear and as you say, quite elementary. But as soon as you refer to spectral basis, it brings to mind a whole lot of machinery that you're not actually using here, right? Right?
Well,
Like,
we could write a multiplication table for the next case, but of course it's much bigger. And well, I'm not doing that, but well, here it
why-
is. That's the multiplication table.
how do you know that this expression 7 is necessarily the spectral basis like that?
Okay, well, look at 6 again. You can get it from this basic rule 6. AI, B, again, multiply by AI, you can get, you're getting all these multiplication from this basic relationship 6, just as we did in the 2-dimensional case. It's exactly the same, but much more complicated. But I'm not going to write a table any more than I want to write out a table for 10 times 10. Well, that's what elementary school kids do. You know, they write out tables for multiplying.
Maybe I'm still not making myself clear. Like, I don't, when you say spectral basis, then I immediately wonder if I should understand when I look at 7, that 7 is necessarily a spectral basis.
Let's look at this element U1 times U2. We know that U1 and U2 are idempotent, and they commute with each other very simply. So if you square that, well, that's just like having a 1 here and zeros everywhere else in the matrix. In fact, this element B1 times U2, if you look at that element, that's B1 times B2 times A2. That's what it is in terms of the nilpotents. We can write it entirely in terms of nilpotents. B1 times U2. Well, here it is. U2 is B2 A2. So it's B1 B2 A2. So I'm identifying all the corresponding elements of a matrix with 1 and everywhere zeros with this element, with a matrix with 1 here and 0 everywhere else, with B1 times. So I'm identifying each element in a matrix, a unit matrix, with the corresponding element in the corresponding geometric algebra. Now you can check that, but of course it's very, and you can prove by induction or, people have introduced these damn geometric algebras in so many different ways with so many different bases, multiplying bases of matrices, but I don't do that. I change it around the other way. I introduce an algebraic space of generalized space of nilpotents. And now I say how to multiply these nilpotents. That's the most basic thing in linear algebra, and not a matrix consisting of n rows and n columns, which you multiply together, which in no sense at all has no definition, geometric definition or anything, which you only get when you start putting on the structure of a Clifford algebra or the Pauli matrices or the Dirac matrices. That's when you're giving these matrices geometric structure. Well, I'm claiming that geometric structure follows from taking Grossman algebras, which are compatible, like in 6 here. That defines the.
But yes, I think that's clear. But how do you know to write the expression on the left-hand side of the equal sign? That is like that. You have that column vector times U1, U2 times the row vector.
Well, let's put it this way.
How do you know that that's what you should write down?
It took me years to figure it out.
but I was looking for Mike.
I can write it in the simplest way. So now of course I tend to write it in the simplest way I can, and this is the simplest way you can write that, and it's all correct. Well, you can verify 7 times 8 is 56, right? Well, okay, you can verify that B1 times U2, B1 times B2 times A2 multiplies exactly as the matrix 0, 1, 0, 0, 0, 0, 0, 0. It obeys exactly the same multiplication rules as this matrix, as a matrix with 0, 1. And in fact, any of these elements you can replace by this corresponding element in the geometric algebra. But who wants to multiply? 9 times 9 is what? 81. 9 times 13. Who wants that, right? We know how to do that. But so what I'm doing here, I'm writing any matrix as a product of nilpotents. And the rules defined for those, okay, I assume I haven't proved it, but I assume the algebra of nilpotents obeys exactly the same rules as the algebra of matrices. And then, okay, everything else can be proved, but who wants to do that? Well, you know, like I say, that's why Clifford algebra has been so confusing, because people do it in many ways with many different identifications. But I think this is really the crux of the matter, what I'm writing down here, which took me years to understand. So we're talking about dual Grossman algebras or compatible Grossman algebras, which can be identified with n by n matrices. Okay, well, let's see here. Okay, so here's the way you write the matrix of it. Take a 2 by 2 real matrix, for example, and take 1, A1, A2, A2, 1, 2. Write these the primitive idempotent U1 times U2, multiply it by the matrix of, you know, the usual 2 by, well, that's 4 by 4 matrix now, and multiply it by this, and you get exactly the geometric number G. Okay, now I try to explain why the Dirac algebra G13. Well-known Dirac matrices can be obtained as a real subalgebra of the 4th cross 4 matrix algebra MAT CO4 over the complex number where J is equal to -1. Denotes the unit imaginary. We first define the idempotent. Okay, well, now I'm using the so-called Dirac algebra. Yeah, G13. Those are the those are the geometric algebra of the Dirac matrices, which we identify with gamma 0, gamma 1, gamma 2, gamma 3. Okay. Notice that if you define I equal to gamma 0, so normally, of course, you would be taking Dirac matrices, gamma 0, gamma 1, gamma 2, gamma 3. That's identified with the geometric pseudoscalar in the geometric algebra G3. This is no longer possible since G0, 1, 2, 3 anti-commutes with the space-time vectors gamma U. Okay, well, the gamma matrix bivector, gamma 1, 2, which Hastings uses to generate spinors in the Dirac algebra, can be written as G gamma 1, gamma 0, gamma 0, gamma 2, because remember, gamma 0 squared is 1, gamma 1 squared is -1, gamma 2 squared is -1, they're including. So we get that as minus anti-commuting gamma 1 and gamma 0 gives minus gamma 1 gamma 0. So that's the same thing as the product of the Pauli matrices 1, 2, 2, 1 here. Well, anyway, it gets more complicated, of course. Okay, so here I'm identifying the spec basis of the Dirac algebra 1, 3. Well, so this is what I'm doing for Dirac matrices. I don't really want to spend, of course, the basic algebras are the mother algebras, which have been called mother algebras with the neutral signature G22 or GNN. Okay, that's where you have n vectors with positive square 1 and n vectors with negative square, called F. I call them E and F to keep them separated. But anyway, it's the same idea.
But
Each of these elements corresponds to an element in the Dirac algebra.
you see,
With
here
1, 0,
again,
0. Okay.
here again, you write the spectral basis,
Yeah,
and
exactly.
you give the expression on the left-hand side, that product of three matrices.
Exactly.
And that I just like, where would I go to understand why the spectral basis is always written as this product of three?
Okay. Well, first of all, it took me a long time to understand how to write, even though you can find in, people do it in the literature. U plus 1 is 1/4. Well, that's an idempotent. 1 minus gamma 0 is an idempotent. 1 plus j. So I wanted to get an expression for the so-called Dirac matrices, but it wasn't clear how to write down this spectral basis. It took me a long time to understand. I didn't even pay attention to the Dirac algebra for many years because, well, for the simple reason that you just said, it's not that easy to find this expression or to verify that it's a multiplication table. But again, it reduces all Dirac matrices to a product of nilpotents because I'm identifying, here you see the geometric algebra G13 is generated by a gamma 0, which has square plus 1, and gamma 1, gamma 2, gamma 3, which have square minus 1, are anti-commuting. But I want to write them now as a product of nilpotents. So it's a part of this generalized nilpotent space, which I defined my first definition, obeying all the rules of usual matrix addition and multiplication. So that's a more basic structure, I think, than 2 by n matrices. The basic structure is the Grossman algebra, as Grossman had it correctly figured out. And now with that new definition of what I mean by compatible, we have 2 compatible Grossman algebras. That generates A1 up to AN. That's the first Grossman, and it's dual compatible Grossman algebra satisfying this relationship. Given those 2 relationships, everything else follows. Again, assuming that we have a generalized algebra of nilpotents. It can be infinite dimensional. In fact, these ideas can be generalized to functional spaces, but a lot of work to be done to understand the best way to do those things. Although many people have done work that's generalized, functional analysis has exploded in terms of Clifford algebra. This Clifford algebra, Clifford analysis community have whole, 400 or 500 page books about functional analysis of generalized Clifford algebras. For Clifford analysis, it's a very highly developed subject by Clifford analysis. But I'm not trying to do that, I've tried to do a little bit of things, but I haven't. It can be very complicated.
Could you show again the spectral basis for the Dirac algebra? Yeah.
Okay, what we have here. So gamma 0, standard.
Okay. Yeah. Oh, no, go.
Dirac.
Could you go back, I guess, to just so that we can see all of 11? Yes. So here, I just want to, I think if I just wanted to point out something here, if I can, let's see if I can do this. So, can you see this annotation that I?
Down at the bottom of my screen, a circle of blue or something. You can write on my.
It's not in the right place. So what I'm. So it's. Yes.
My
This,
right bottom screen, so you'd have to move it up.
so this, I'm not sure quite what happens there, but
We're talking about 11, though, right? That matrix in there.
yeah, that expression on the left-hand side of the equal sign.
Right here.
Yeah,
That's right.
it always has this form, but in the case of the Dirac algebra, there's something else going on here, right? Because you have like, like E13 occurs with a minus sign.
Well, if it was 1, then it would be E13 is minus E31. Okay.
But if you skip back to your previous spectral basis, then like for G22, I guess. So here we have like A1 and B1 and A2 and B2, right? But in the Dirac algebra, you had E13 and minus E13. Like it's.
Yeah, so I'm referring back to G3 then. I'm defining the Grossman algebra in terms of an observer, E1, E2, E3 of an observer.
But I still am looking for kind of a meaning for this, for the factors on the left-hand side. Like so the first factor is this column vector, and then there's a matrix, and then there's a row vector. And so it seems peculiar that in the Dirac algebra case, the row vector is so closely related to the column vector, but in the other cases, they were apparently independent.
Well, there's no real difference, but the thing is we're dealing with different signatures, and it means that you have to complexify it. Well, for example, the Dirac matrices are complex matrices. So there's all kinds of things going on with the complex matrices. But here are the idempotents. U plus is, well, where is it? Yeah, U plus plus, this is one idempotent, 1/2, 1 plus gamma 0. That's an idempotent. And 1 plus J times gamma 1, 2. Okay, J is assumed again to be -1, the square root of -1. It commutes with all these elements because it's in the center of the algebra again. So again, it allows a complete geometric interpretation of Dirac matrices. And of course, that's exactly what Hesnes is doing in all his papers using space-time algebra, he calls it.
But this idea of partitioning unity, that's the way you wrote it here. You said that they.
Notice that unity in this case in 11 is the sum of the diagonal elements. U plus plus.
Yes, the trace.
Minus plus. That's what is equal to 1. The sum of ones, all the diagonal, is 1.
That was true in all of your cases, right?
That's right. The diagonal matrix then becomes a unit.
So the trace of the spectral basis is 1, right?
Yeah, that's right.
And that's sort of some kind of general statement about what you mean by spectral, right? Spectral basis, right?
Yeah, I've been using that terminology for years. I never knew it was completely appropriate, but I used it because, well, a matrix, they talk a lot about the spectrum of a matrix being the solutions of the characteristic equation. So I don't know.
Exactly. Yes.
Yeah.
So when I read that, that's what immediately came to mind is that little corner of mathematics where we're.
That's right. And of course, when you diagonalize a matrix, the elements appear on the spectral basis, or becomes a diagonal matrix of the eigenvalues. So another reason why I use the term spectral. Of course, most matrices can be diagonalized. I don't know. Anyway, I chose that terminology for spectral basis. Okay, but anyway, so the complex Dirac matrices are exactly identified in this way using 11 are exactly the usual. So, you know, you take sigma 1 along the diagonal with the minus sign. These are the usual standard Dirac matrices then, defined in terms of, oh, but notice this thing. Again, that F in the E2, that J times F is E2, sigma 2 for the Pauli matrices, you know, where the Dirac matrices are defined in terms of the Pauli matrices. Well, that's the equivalent of that idea. The second order 2 by 2 matrix of E2 is I times 0 minus 1, 0, but that's not the same thing as J times 0 minus 1, 0. So again, the reference I give is my book again, which is very expensive. I think I sent you copies of it anyway, so you have copies of it. You can find more details in my book, but notice A1 plus B1, and these are the nilpotents and how it relates to, but again, it's difficult to go through all the calculations because that's why it's nice to use a neutral signature, because the calculations are much, you don't have to worry about complexifying this term or that term. You know, it becomes complicated, but here it is again, the spectral basis in terms of the nilpotents. Notice that.
But this is a new basis, right?
U2 is B2A2. But notice what I'm doing here is I'm complexifying that. So it's another way of identifying the standard basis in terms of just the complexified 2 by 2 case. So, okay. Anyway, you know, okay, I wanted to mention, at least mention this. So again, I'm quoting out of my book, this book here that is not very famous at all. I published it myself. I didn't wait for Springer. As I say, I had submitted it to Springer to publish it, but after 6 months, I heard nothing from him, at which point I decided to publish it myself. After I published it myself, Springer said it was accepted. But I told him, well, I've already published it, so, you know, nothing to talk about. But as a result, I could make it very cheap. Instead of making it $50, I might raise the price again because I don't know, you know. But at least I'm the one that sets the prices. I like it to be. Oh, by the way, I might mention the conference called ICACGA. That's a conference taking place in October. You might look it up. Hestes is the main speaker. I have submitted a paper which has been accepted to that conference. It's in October. I can send you the exact webpage on that. You might want to attend that conference. Hestes is the honored guest speaker for the whole conference. It's the applications to computer science, robotics. It's the other, you know, a lot of more Clifford algebra is recognized in the in the computer science community, graphics and all that, than in the pure mathematics side of things. So this is a conference that's devoted to applications to computer vision, so I'm going to be attending that conference. I've been accepted to give a talk too, but Hestes is the main honcho, if you want to call it that, that's being honored as the main. There are a bunch of speakers as well. You might want to look that up. I can I can send you the second now. I try to find it. Let's see here. Well, anyway, I think it's ICA CGA, or I think that's what it's called. I'll send you the reference to the conference. It's,
Sure.
let's see here. Yeah, it's ICA CGA. That's correct what I said. ICA CGA. Just type it into Google and you can find the web page of the conference. It's called ICA CGA 2022. That's the name of the conference. Okay. Okay, well, let me, classical Dirac spinners. I give a page reference. Again, this basic idea. Well, now you can identify a Dirac spinner by a common matrix, sigma 1, sigma 2, sigma 3, sigma, or I guess that, what is that? Psi 1, I guess, psi 1, psi 2, psi 6, psi 4. You can identify that with the matrix, just with the first column non-zero and everything else zero. That can be identified as a Dirac spinner. That's what people do. Hestes does that. Lunesco does that. Other people do that. Well, we're making that identification, then the Dirac spinner can be represented in terms of this times the U++. Well, I'm not going to go into any details here, but I would like to. Well, anyway, I'm not going to. I would like to get to this last section here. Oh, let's see here what I have. I think I sent this to you. I think you have a copy of this. But
Yes,
what
that
I
was
have-
up to this point. Yeah.
You don't have this last section because I just wrote that.
Yeah.
And okay, I call that complex Minkowski space-time in G23. So G23, you can identify that with G22 complexified. So G23 is the same thing as G22 over the complex numbers, where the pseudoscalar element is defined to be E12 times F123. And we make the identification gamma 0, gamma 2, and so on like that. Wait a minute now.
That's interesting that you make reference to that experimental result that you just July 20. That's I was just reading that, a brief report of that. Yeah.
Oh yeah, so I'm really speculating on this last page. I'm saying that that actually think of double split experiment, you can identify these polyvectors in a different way. In fact, the polyvector, as we saw, can be in a different algebra, can be interpreted by, for example, in this case, a vector is being interpreted as a Dirac trivector. And I'm saying that if you interpret it in this way, I'm distinguishing when a particle is entangled. I'm saying that's when you use this interpretation where the polyalgebra for representing E3, I'm calling it E3 prime, is a trivector of Ryan element. In a certain sense, I'm thinking about Professor or Dr. Santilli's idea of his generalized Dirac algebras, or iso-Clifford algebras, where a trivector plays an important role. So anyway, I can send you this new version. I haven't sent you that yet because.
Yeah, this is, I think, getting very interesting at this point. I mean, it's
it's total
Of course.
speculation on my part, but it
Yes.
seems.
Of course, it's speculative, but this notion that there's something more complicated about time in this particular.
Well, actually, I had just come across a paper saying they think maybe a second time dimension is necessary. So I started thinking about that idea, and I came up with this new identification of Pauling matrices. So I identified that with entangled particles. And the reason why in the double slit experiment you never observe an entangled particle is because it's in the fifth dimension. Simple enough. So I can send you a copy of this new version here, which is the interesting page I wanted to at least talk about a little bit. So I talk about this, and I added a new reference, namely the last. Oh, yeah, I think it's in this dynamical topological entrapped ion quantum simulator. Well, that's where he's saying he needs a second time-like dimension. So that's what inspired this thinking about it. So that's basically, I think all I can say, really, all I want to say. Is Dr. Santilli still on? Maybe he signed off.
Unfortunately, I think he said he would be interrupted by a storm that was occurring in Florida. So
okay, well, I'll send you, all of you, all the people. I guess it's just you, Bill Page, Dr. Cruz, and that's all. And Dr.
Yes.
Okay, so I'll send you all this.
so so this work is still work in progress. Do you continue?
Yeah, I'd like to get back to it, but lately I've been distracted by, there's a deadline. I have to turn in my final version for this ICA CGA conference on the 10th. So I've been trying to finish my paper up for it's accepted. I have to pay attention to the reviewers' comments. So I'm working on that. But you might want to look at that. To attend the conference virtually, I think they're charging $150, ICA CGA 2022, but it's going to have all kinds of applications. Hestonese, again, is the major, most important speaker, and then there's a lot of other applied speakers in computer science. They invited me to give a talk, which will be basically related to what I've told you today. I do it in, well, I was inspired by Dr. Ojevich's. I might have even talked about some of it in this conference. So I've made that into a paper. I can send you a copy of my, I haven't submitted it to RX, but it will be, they've accepted it for publication in the proceedings of this ICA CGA. So you might look at the webpage for you can get an idea of the full scope of the conference and who's going to be talking.
Okay. It sounds interesting, but it seems now that we're so used to meeting virtually like this, it seems unusual to be asked to pay a substantial fee to participate.
If you want to go to the conference, it costs much more, and it's $400. I forget what it is. It's very expensive, actually. So.
I mean, actually, to be physically on site, you mean? Yes.
Yeah, I agree. I agree. They should open it up. In fact, if they hadn't accepted my paper, I would be going to it myself. In a way, you know, my book with Hestonese, he's basically been given credit for the whole damn book, even though it was based, a good half the book is based on my thesis. I don't think he gives me credit for my own work in linear. When I was a student, he was telling me all kinds of differential geometry, this, differential geometry, that. But my thesis is basically linear algebra, developing the ideas in linear algebra, and which is exactly what I'm doing since that time. But anyway, Hesnes is only 10 years older than I am, and he had just come to ASU. My father advised me about working with a young, unestablished physicist, that such complications and disagreements could come in place. We had our paper, was supposedly we were going to publish 4 papers based on results in my thesis, but they were all rejected. Okay, so then Hesne says, okay, we'll turn it into a book. Well, he basically, at that time, I was out of a job, and it took 10 years for the book to be published. And it's a long story. I'm not going to get into that.
Yes. No.
But
I'm glad that you're making this material available now in this Gateway book, and I hope you have success with distributing it widely.
Well, one reason why I want to fork over the $150 for this virtual attendance, I am invited also to give a talk. I don't know anything about how long or whatever, but it's because it's advertisement for my book.
Sure, why not?
The book has actually done pretty well. I've received, but again, since I had published it independently, lots of people are skeptical about buying books which are, independently published, for good reason, as far as that goes. But anyway.
You need someone to take it up as a textbook in a course somewhere.
Yeah. Actually, Springer has invited me to publish a second edition of it or whatever with them, but I'm not even sure I'm going to do that. I'd rather publish it independently. Well, I have some new ideas, but a lot of the material I'm presenting is developed. Remember, I published this book basically in 2020, so it's pretty new. It was at the end of 2019, so it's pretty up to date. But I think I have developed it a little bit better now, thanks to this seminar, the research seminar. And I will certainly give. I am very grateful that they invited me to be a principal speaker in Dr. Ojevich's memorial conference organized by Jesus Cruz and Hilda Guzman.
Yeah, I hope things are progressing with the publication of the memorial volume. I hope that that goes ahead quickly.
Yes, I think we are almost at the finish of the preparation of this volume, but some technical problems with some works ended to us. But I think that in short time we can arrange all of this. But yes, after almost 1 year, we are arriving to the end of this.
Well, I know it was, I had a lot of trouble with technical problems myself, but I am very appreciative of this research seminar. It kept me busy. I was ready to quit altogether, but actually it's been very helpful being able to talk to all of you, mostly.
There are, I've noticed where the videos are being stored on YouTube, it does show me statistics of the number of times presentations have been downloaded, and the numbers are small but growing. So, so I think.
Well, that might be a reason to attend. Like I'm going to, it's true that they say they will give me an opportunity to speak, and also they'll publish my paper. Otherwise, I wouldn't be spending $150 on it myself. I mean, you know, in a certain sense, I think I've been ignored. Hesnes gets all, well, Hesnes has done a lot of work besides our book in introducing it to computer science and all. I respect that, but as far as our book is concerned, I'm not happy with the way that's generally treated to Hesnes without me. I've seen it even addressed as Hestes, leaving out my co-author, Garret Sobczyk.
I'm sorry that that's occurring, but
well, it happens all the time. It's a cat eat dog world, scientific publishers too.
Yes, I suppose. Okay, well, thank you very much for the discussion today. I think it was very interesting indeed, and I personally am going to be spending more time sort of following it up. And I like at this point where you ended with the very current reference to possible application. I think that's very valuable and motivating.
So I just might say, you might join that conference it'll advertise our research seminar as well. Might get more people interested in that.
Sure. Yeah.
So look at the webpage. It's ICA CGA 2022. And I'm certainly looking forward to seeing the completion of the Ojevich Memorial Book too. I know it's been a lot of work, and for organizers especially, to getting it together. But I've enjoyed it. And I appreciate that I was invited it's kept me going. I might have retired, just given up and, you know, just quit the whole thing.
Well, don't do that yet.
Well, these years are creeping up, you know, they pile up, as you know.
They certainly do. I think we should probably say this goodbye today. But before we do, I suppose that our current schedule of meeting every 2 weeks is still appropriate, but we don't have a fixed subject yet for 2 weeks' time. Eustace, did you have sort of some place that, you know, like some comments that you would like to extend on interaction theory? I know you started to discuss observers. That there was a reference to observers, and I think so far that is not strongly connected to the material that you presented earlier about interaction.
Okay, yes, it will be nice to speak to prepare something about this. Then I can present this in 2 weeks.
I like maybe if you have the opportunity to review, to sort of maybe begin your comments in 2 weeks with a review of what you were discussing a few weeks ago about observers, and the observer algebra. I mean, that is something that has fascinated me for a long time. And I think the structure of that observer algebra that you and Oshevich were analyzing could be viewed perhaps, you know, from the point of view of geometric algebra. I'm not sure, but it looks promising that especially these developments that Garret has presented today suggest fairly strongly that there may be a way of viewing this observer algebra in geometric terms of the kind that he's presenting. So if
write a paper and nail down this relationship that we're talking about, like these three observers, how that arises in Oshevich's ideas is still a mystery to me.
Okay.
Okay, of course, I am going to prepare something. I am going to review the presentation of the 2 weeks ago, and then in that line, I'm going to prepare my next presentation.
Perfect. Okay. Well, I'll see you in 2 weeks' time.
Okay, thank you. Thank you very much.
Bye for now.
Bye.
Take care. Bye.